Hello, this is Ryan Campbell in Dr. Jiang's MEE 322 Structural Mechanics class with my honors contract on stress transformation with combined loading. So I want to start out with just a general idea of what we're trying to accomplish here. So if you have an axis, let's say X and Y, and you have a unit vector along that axis, E1 in the X direction, and E2 in the Y direction. And then let's say you've got some vector V. The equation for this vector V, based on our current coordinate system, let's just say V equals, let's say this is 1 unit over and 3 units up. So you've got 1 E1 plus 3 E2. And that's just the equation that denotes this line here. Now, if we establish a new coordinate system superimposed over that old coordinate system, so let's say we've got now X prime and Y prime, the equation for this vector V can no longer be described as 1E1 plus 3E2 because its location with respect to the new coordinate system has changed. Even though its magnitude and its physical location has not changed, we need a new equation to denote it. So applying that to stress transformation, we've got our axis again. Let me drop it a little better. That's not better. There we go. X and Y. And we'll put our unit vectors in again. E1, E2. And let's say our stress is represented by this box here. So you have stress in the X direction coming out the right side of the box, stress in the Y direction coming out the top of the box, and shear along the side. Now, if we rotate, establish a new set of axes that is rotated from the original, call it X prime and Y prime again. If we rotate it some angle theta, our stress rotates along with it, and this is the new way to denote our stress given the new coordinate system. Just like with the vector, we now need a new way to identify it. So stress in the X direction is still coming out the right side of the box. Stress in the Y direction is still coming out the top. And shear is still along this side. But they are all denoted with this prime value here, which says this is a new way of representing the same magnitude of values just along a newly identified coordinate system. So here we are again with our rotated axis just like before, and we need a way to describe E1 prime and E2 prime, which are now along these new axes. So just like before, where we had E1 and E2, now we are looking at the x-axis being rotated some angle theta, as well as the y-axis being rotated some angle theta. So this x distance here is cosine E1. So we're going to write that right here to denote the new x value of x prime here. So the new E1 prime x value. So cosine theta E1 plus, and then the y value is going to be represented by sine theta E2. Now moving on to the equation for E2 prime, the x distance is now the side opposite this angle, so we're going to need to use sine theta E1 to denote it, but since it is in the negative x direction, the sign on it has to be negative. Now looking in the y direction is the adjacent side to this angle here, so we're going to denote it with cosine theta E2, and since it's in the positive y direction, the cosine is also positive. So writing those equations in matrix form, E1 prime, E2 prime, equals cosine theta, sine theta, negative sine theta, cosine theta, E1, E2. And that's just rewriting these two equations for E1 prime and E2 prime in matrix form. And what's really important here is this matrix right here, and we call it the directional cosine, and it is denoted by beta. Just as a quick side note, beta in 3D is very similar. And let's say you want to rotate, just like previously we have rotated up an angle theta, but this was just in 2D. So let's say if you were in 3D and you want to rotate about the z-axis, you put a 1 in the placeholder for the z, zeros in the corresponding rows and columns, and the same cosine theta, sine theta, negative sine theta, cosine theta in the remaining places. This equation also works for 3D, the equation I'm about to give you, but for this video we're going to focus on the 2D cases for the examples. So that equation, to get the new stress matrix, is your directional cosine times your original stress matrix times the transpose of the directional cosine matrix. What that looks like written out is you've got your new stress in the x, your new shear in both of those places, and your new stress in the y, equaling your directional cosine times your original stress matrix So that is this equation here written out with all of the matrix rather than the variables that denote them. So taking a look at an example of how to apply that for a 2D case, of course. You've got a stress matrix, and we'll say that that's equal to 3, 5, 5, 4. And let's say you want to rotate your axis an angle of 30 degrees. So your new stress matrix will equal your directional cosine, so cosine of our angle 30, sine of our angle 30, negative sine of our angle 30, cosine of our angle 30, times our original stress matrix, 3, 5, 5, 4, times the transpose of our directional cosine. So cosine of 30 negative sine 30 sine 30 cosine 30. And when you punch that into a calculator, it will spit out the matrix 7.58, 2.93, 2.93, negative 0.58. So that is our new stress matrix. If you want just any single component of that stress matrix, most often we have been asked for the new stress in the x direction. And that the equation for just that component is original stress in the x plus original stress in the y divided by 2 plus original stress in the x minus original stress in the y divided by 2 times the cosine of 2 times our rotational angle plus the shear times the sine of 2 times our rotational angle. And that was what we were given in class. And there are two other equations for stress in the y direction and shear that we were not given in class, but those are denoted by stress in the y equals stress in the x plus stress in the y over 2 minus stress in the x minus stress in the y over 2 cosine theta minus shear times the sine of 2 times our angle. And then our new shear is equal to negative original stress in the x minus original stress in the y divided by 2, and I'm going to put some parentheses around those to make it clear that that negative applies to that whole value, times the sine of 2 theta plus our original shear times the cosine of 2 theta. So applying that same example with 3, 5, 5, 4 equaling shear and our angle is 30. Stress in the x, our new stress in the x is equal to 3 plus 4 divided by 2 plus 3 minus 4 divided by 2 times the cosine of 2 times 30 plus 5 times the sine of 2 times our angle 30. And that comes out to 7.58. Stress in the y equaling 3 plus 4 divided by 2 minus 3 minus 4 divided by 2 cosine of 2 times our angle 30 minus 5 times the sine of 2 times our angle 30. And that gives us an answer of negative 0.58. And for our new shear, got negative 3 minus 4 divided by 2 sine of 2 times 30 plus 5 times the cosine of 2 times 30. And that gives us 2.93. So these three values here, take notice that those three values correspond with the values we got in our matrix up here using this equation here. This just got us the entire matrix, whereas using these equations got us each of its specific components, but the exact same answers. That's it for my video. Hope you all enjoyed and learned or reinforced what we learned.